Methane is 20 times worse than CO2 as a greenhouse gas, so when it's created as a byproduct in oil rigs, it's burned. This is better than releasing the methane into the atmosphere, but it's not an ideal solution as it creates more CO2. Jerome van Bokhoven and his team at ETH Zurich have found a new way to convert the methane into something cleaner and a bit more useful. I found out what it's being turned into.
We form it into methanol. Methanol itself is a resource for many chemicals. We can even convert this to fuels in the end. So it is methanol is a base chemical which finds many different applications.
Is methane generally quite a reactive substance?
Methane is a rather unreactive substance. One of the difficulties to activate methane is the product that you make, the methanol, is more reactive than the methane itself. And that's why this reaction is so difficult to perform selective, because the methanol will react further and then you will not end up with a useful product. And that's why this reaction is called the dream reaction, because it's so difficult to perform and achieve a high yield.
How do you do this? How do you convert this methane into methanol?
Well, we defined a stepwise process where we have a material which we activate, and this activated material is then reacting with methane. And then we switch the conditions, and then we have the activated methane reacting with water, and this generates the methanol, and at the same time reactivates the material so it can react with another molecule of methane. And the novelty is that we use the water, and the oxygen from the water molecule ends up in the methanol. And the previous methods that have been used will always use an oxidant. The novelty here is that we use the water, which simplifies the process very much.
Before your discovery, how do we currently convert methane into methanol?
Currently, that is a very involved process. There is two large-scale processes involved. One is the steam reforming of methane, making syngas, that is carbon monoxide and hydrogen. This is a high-temperature, high-pressure process. And then in a second step, this mixture is reacted over a novel catalyst to methanol. And this is only commercially viable if it's done at large scale. And that's why at smaller scales the methane is not viable to convert into methanol. So that's why it's burned. And our process, we envision that you can do it at much smaller scales, and then it would be profitable to do it that way.
So is that sort of the end goal here, is to use your process at these oil well sites where currently methane is just being burnt as flares, and you're saying, well, no, what we can do is ideally at these sites convert this to methanol and then do something useful with it?
Yes, that is correct. Yeah, it's to do something useful with which is now considered a waste product.
How far away are you from that? You know, like what would a setup to do your process sort of look like at, for example, at a well site?
Well, at the moment we are far from a commercial and an actual application. When we have shown that the concept works on a very small scale, and the next steps in the lab is to scale up this process as well as to make sure that the rates of reaction, so the speed that the reactions run, are sufficient for a large-scale operation.
And when you say you've done this in the lab, like how much of this methanol are you making? Is it really, really quite small amounts currently then?
At the moment it is really small amounts, yes. But we also have not optimized this at all. Mm-hmm. So there is huge opportunities for optimization. We have shown the proof of concept. That's what the paper is about. And of course the next steps is to understand what the chemical mechanism is better than we do now, and as well as direct trying to scale this up. And there is huge opportunities to do the scale up. But the research is not in the stage that we have looked at that. That is really the next thing to do.